Yeah. At least for prepared. No.
Just. Okay, let's continue from here. We did this in the last class. Very guaranteed. The three types of interferences, this we know. Spectral interferences, chemical interferences, physical interferences. All right. We stepped through this last time on the spectral interferences and what they are. You can see you can have a spectral overlap. The lines can overlap. You can choose a line which is not absorbing. And sometimes you can have molecules also that can absorb at that particular line, which means if that happens, then you don't get the correct concentration because the concentration is enhanced. And then you can also have some light scatter from outside that can enhance some the wavelength of absorption. Now, we also talked about what we need to do in order for us to, in case you have chemical interferences where you have a stable compound formation. I mentioned the oxides in particular. You need to use a hotter flame, increase the flame temperature. Instead of using acetylene flame, you can use, let's say, a nitrous oxide flame, such that you have a hotter flame, a higher temperature, or you use releasing agents. And I give some, I do not give examples there. I only say that releasing agents are going to react with the compound and release the atoms there. And then you can do some separation. Okay, you can do separation by having another method up front. Okay. It's that season of the year. Okay. So you have ionization is the other. Remember, we've talked about this first one here is a stable compound formation as one of the chemical interferences. We have ionization. And in here, I gave an example of group 1 metals, potassium, if you remember, you wrote these down, okay, such that you shift the equilibrium to have the atoms, okay? And physical interferences can also occur where we compete with viscosity. That means if you don't match your solvents where you dissolve your compounds, then, or where you dissolve the sample in which the metal is, then you're going to have to deal with this, okay? Okay. And so you can have surface tension, and also if the compound volatilizes, it means then if it is becoming vapor, so then you need to put it in atomic, you're losing some before you do the atomization. So what you need to do here for all this is to do matrix matching, like what we do. Everyone has done HPLC except a few. How many have not done HPLC yet? There's one group I know who have not done HPLC. Remember, in HPLC, what you do, if I make people prepare 70 to 30, right? And that's the solvent you use. That's like matrix matching. So if you're preparing your solution in one, if it's water, 1% nitric acid, then you need to use the same for the solvent that you're using. Are we together there? So it's the same kind of thing on matrix matching. such that you reduce volatility, surface tension, the density becomes similar, and viscosity will be the same, such that it moves through at the same time. Okay, now preliminaries here. The preliminaries usually, what do you do when you are preparing samples for analysis? This is general, and for all the kind of techniques that we deal with, you have to prepare your standard sample solutions. And the next thing you do once you prepare your standard solutions, you need to optimize the operating conditions. Most of the experiments that we tell you, we just give you those, okay, use these kind of parameters, but in the lab, you have to optimize those, okay? So critical to the analysis will be choosing the correct resonance line. Remember, AA depends on choosing the correct resonance line, all right? And then it's important. And if you don't know the resonance line, if it's a new compound, then you have to play around with those resonance lines. There are resonance lines are known, as I'm going to mention today. There are many, so you can choose others and see if they give you the desired concentrations. You can also have the slit width. Choose the slit width. Slit width is going to allow you to control the amount of light that goes into the sample. If it's too narrow, you may not see the concentration. Increase that to give you a signal. The current of the HCl, that is the hollow cathode lamp. And remember, last time I passed the hollow cathode lamp, you saw it black. It means we've been using it for some time. The current, the atoms have been bombarding the walls of the hollow cathode lamp. So slit width, resonance line, and the current of the hollow cathode lamp, and the atomization condition in case of the graphite furnace. And those are the three things that we deal with first. Preparation of samples, optimize your operating conditions. Number three, you make a calibration curve, like what we have done. All right? You make a calibration curve, and from the calibration curve, and then you will then determine your concentration. Note, this is the things that we do. And when we do the experiment in the lab, some of you are going to have difficulty in terms of understanding what is happening. But I think I have a video that I'm going to put there so that you get to follow what we do. So here are other ways that we deal with, just like normal analysis in the lab. If you have matrix interference, notice the word I'm using, matrix interference. If there is matrix interference, you can use the standard addition technique. And notice the standard addition technique. Sometimes I give a question in an exam where you have to draw a calibration curve. So that means there is something in your sample responding even before it is zero. I mean, there is something within your sample giving you a response. If it is zero, you can see. If it is zero, at zero here, you see this is zero. Zero, you expect a response that is zero. Are we together there? But then it responds. That's telling you there is, within the matrix, there is something that is also absorbing. So how would you determine the correct concentration of your analyte? Remember, at zero, if there is no concentration of your analyte, something is absorbing. So what you do, which you have learned in quant, your previous class, is for you to prepare a solution, spike it with a given standard of known concentrations. Are we together there? So this is the first concentration you see here, the second one, and the third one, the fourth. So for example, you can increase the concentration linearly, 5 ppm, 10 ppm, 20 ppm, all right? Which means the analyte response would increase linearly. So that's what you are seeing there on those checks that I've made on those concentrations. And then what you do is you extrapolate it to all the way to zero. So you see the dashed line, then there is a question mark here, and that is what this is. Therefore, what you're having here is now this question number 2, 1, 2, like a question mark here. That is the true concentration without the matrix interference. You extrapolate it to zero, and you have these questions. in your textbook, asking you to plot. So let's get to it. When we use standard addition techniques, the one word that I use, two words, when you have what? Matrix interference, because the matrix is absorbing. And that is standard. When you hear the word standard addition, it comes with that word, matrix interference. Okay. So make sure you note that. So let's define some terms here that we normally use, which we have come across, but especially for this, we are going to just change it a little bit for AA. Notice the word sensitivity. Now tell me, what is sensitivity as you know it? The one word that comes to mind when we talk about sensitivity. Sensitivity. It refers to the change, right? With a given concentration. What is that? A slope. Is that not the case? It's just a slope. Because some compounds are more sensitive. They respond very fast. So in this case, notice how we define. We define this in two ways in AA. It's the concentration of an aqueous solution of the element which absorbs 1% of the incident resonance radiation. This is specific for AA. We define it as that concentration in an aqueous solution that absorbs 1% of the incident radiation. The resonance radiation corresponds to the wavelength. So it's 1%. If it absorbs 1%, remember that is sensitivity, 1%, that means 99% it can be transmitted. So that is just by definition that we have come with, but you will see a familiar term that you may usually identify with is this one in AA is the concentration, which gives an absorbance of 0.0044. You might want to think about that. An absorbance of 0.44, take your calculators for me, please, minus log T, so which means 0.0044 equals to minus log T, which simply means that T is equal to 10 raised to minus 0.0044. What number do you get? How much is transmitted? Just take your calculator, because it comes from there. This number comes from how much is transmitted. How much? 0.9? So that's what it corresponds to, 99%, right? Which is 3 sigmas, just like what we have defined it. Remember how we defined the slope, all right? And we said 3s over m. How did we define that? Remember how we defined that? What was that again? What who remembers? Limit of detection. That's what that is. So you're telling us, so you're telling somebody, if you want 99%, you're going to the limit of detection. That's how we define it, like this. Does that make sense? I hope that is clear to everyone. We're just going to the limit of detection, and we're defining the concentration, which gives an absorbance of 0.0044. Again, those are the numbers that we go with. Okay, so now, again, limit of detection is what the next slide here is. Remember, the first one is just sensitivity. We are defining sensitivity in this manner. And now we go to the next part here, the detection limit, which is simply, which you all know, we have already defined it, is 3s over m, right? Where A, in this case, A, where m is the slope. We've defined as this. Okay, this one here is just the blank, the concentration of the blank. If you go back, Remember, that's how we defined it, the concentration of the blank, the very lowest concentration. Does that make sense? So typically, we define it as detection limit is equal to 3s, where it's the standard deviation of the curve, over m, which is the slope. If you deal with environmental samples, sometimes we'll talk about 3.33. 3.3, you're going to see that number as well. But this is our general definition. So let's get to this. It is the lowest concentration, remember, the limit of detection, lowest concentration of an analyte that can be distinguished with reasonable confidence from a field blank. That's just a definition. But then when you use an equation, it's D equals to concentration of the blank. This is the blank times 3 sigmas. That is 3 standard deviations or sigmas if you have so many population over A. That's the absorbance or just the slope. Okay, that's the general, as we define it. So those are terms applicable to AA, just like any other methods that you're going to deal with, whether you're dealing with HPLC, if you deal with IR, you deal with UVVs. Again, those are the general terms. We are applying them very specifically. Okay, and we come back again, we shuttle back to the advantages and disadvantages of AA and graphite furnace and A-flame AA in this case. Look at these advantages. Look at the advantages first. AA in general has very high sensitivity. It's high sensitivity. And notice high sensitivity, if you're dealing with flame AA, you can go to 10 to the minus 10 grams past the nanograms. Are we together there? So that's a sensitivity, although we can push it further with other methods, but that is good. And then you have, if you're dealing with non-flame, for example, graphite furnace, it can go greater than 10 to the minus 14 grams. So that is the sensitivity. How low a concentration you can measure. And then it has very good accuracy. Each one of us is going to do an AA experiment, and I'm going to see the R squared value on how you make your dilutions. Usually it's very high accuracy, usually a reliable error of 0.1 to about 0.5. You don't get many methods that are reproducible. In other words, when you do the AA experiment, if you have done very good pipetting technique, you're going to get 0.999 sometimes in the third digit, the fourth. Are we together there? So we're saying about 5%. Remember, this is 0.5%. 0.5% means what? 99 point what? 5. That's very high accuracy for any method, or even 0.1. So when you do your measurements with AA, that's how accurate you can be. It can also, flame AA can be very precise as well. And it has very high selectivity. By selectivity, we mean you can determine the concentration of potassium, calcium, lead without any interferences. You have to do some optimization. So the other one is highly widely used. But I want you to notice, remember the disadvantages of graphite AA, but here we're giving the general advantages. But disadvantages, every time you have to do AA, you have to choose a lamp. If you are doing the 72 elements on the periodic table, how many lamps do you need? 72. And then the preparations, it's going to take you some time. So you have to spend a long time there. And like other methods that we talk about in chapter 10 on inductively coupled plasma. So a resonance line source is required for each element to be determined. In today's class, I will get there to show you this. Okay, that's the end. I've summarized. Remember the first part of AA? I give you an overview and I've summarized it. Those are the important parts. Are we together there? Now I'm going to some little details here and there and key you in on some of the things that I've done. In fact, if I was to stop here, I would go to chapter number 9. Are we together? But I take the liberty to go through some of the details to make you understand some of this. So move on to the next part, is the same chapter, and make sure you pay attention to these questions. These questions are on calculating the population of the atoms in the excited state, and those kinds of things that one of them at least, and then you have the graphs that go with it. Now, I introduced this in the very first chapter. I said three atomic methods, spectroscopic methods, optical spectroscopy, mass spectrometry. Those are just atomic spectrometry. Remember, we are not using spectroscopy here, spectrometry, okay? Atomic spectrometric techniques. Optical spectrometry, mass spectrometry, and X-ray spectroscopy. And we said here, these are the things that I've talked about in the last slide. That is, in each of these methods, you have to prepare your sample. In optical methods, prepare your sample. You have all done this in optical methods. Your sample is atomized in atomic spectroscopy. And then you have gas phase atoms or ions, but more specifically, we need atoms in AA. And there is also, in optical methods, you can also have emission like what we have on XRF, X-ray fluorescence. Okay, so you may not know some of this, but those are, in optical methods, you atomize the sample. You can have gas phase atoms or ions. In the case of fluorescence, atomic fluorescence, those atoms come from the excited state, they come to the ground state. In mass spectrometry, as you may know, we're going to spend time on chapter 20 here. You have the cation, you ionize the atoms, and you measure mass to charge ratio. That's what you measure. Sometimes we abbreviate it as ME or MZ, okay? So that's what we measure, mass to charge ratio. And then in X-rays, usually we say it's an intrinsic data. What do we mean by intrinsic data? Anybody who has worked with X-rays here? Anybody? Nobody. So it's an intrinsic data in the sense that, see, you eject an electron from the inner shell, you eject it, and the electron from the outer shell falls back to fill whatever has been ejected, which means you can measure that energy. And that is specific. The amount of energy that is ejected from the inner shell and is specific for every element, okay? So we deal with that. And it's a direct measurement, okay? So again, here is where I want to spend time again to give you new information. You may have done this on the energy level diagram and the atomic line width. We have mentioned that atomic line widths are narrow. Remember? What order did we give the narrowness of that width? Remember the number? Flashback. What's the width of the atomic line? Please go back. .2. Yes, 0.2 or 0.002 nanometers, right? So that's the line width. So within that narrow, that's why Walsh came up with the what? The hollow cathode lamp, to correct for that. So we'll talk about the atomic line width, we'll talk about the thermal effects, and then sometimes you see a band. Let's get to the atomic energy levels. I know you might have covered this in physical chemistry, or in Gen Chem 1, Gen Chem 2, when we deal with the electron configuration, it all goes back. So let's go here. Look at this. Energy levels, usually every element has a unique set of atomic orbital levels. Every element has its atomic configuration. The orbitals are very unique. And hydrogen is the very simplest. It has a very simple energy level diagram. And because it has only one proton, one electron, that's a two-body problem. But when you go past one, then you go to helium, and you start having many more collisions in many more configurations. Other elements will have complex atomic orbitals, p orbitals, d orbitals, f orbitals, and so forth. And so what we talk about, I'm sure you might have mentioned this, that we have a splitting. We have what we call the electrons spin. As they spin, they interact with the orbits. So there's what we call the levels will be split by the spin-orbit coupling. The electrons spin in a given orbit, so there is spin-orbit coupling. And usually we come up with an energy level diagram, and we want to see an energy level diagram is simply a picture of relative energy levels of an atom. So here, notice what we have. This is a very simple atomic line spectrum for hydrogen. And hopefully you remember, you don't have to remember all the names, but people dealt with this. First of all, you know it's a 1s1. 1s1 ground state. So you excite that one electron to the next s or the next p, next d, are we together there? And they can go to various energy levels. That's what you see here. And that is n equals to 2, n equals to 3, n equals to 4, and so forth. And those are energy levels that can come down, okay? Then the electrons in the excited state can come down. It's the same thing with atoms. You can excite them to given energy levels. So we are using electrons here to show us the complication of all the lines. Remember, we've talked about choosing a line, a resonance line. Let's talk about spin-orbit coupling here. Refresh your mind. So here, the spin is denoted by letter S. The orbital, remember the orbital quantum number, spin quantum number, remember that? Is the orbit, or the orbital rather, we have S orbital, P, we denote it with the letter L. So the spin and orbital motion are going to create a magnetic field that perturb each other. And so this is what we have here on this diagram. You see, on this diagram here, you have the orbit, you have an electron. You have an electron here, for example, you're seeing the electron. The electron is spinning. Notice it can have high energy or low energy. So in this case, if it is spinning, we talk about a J value. And the J value simply means, we need to mention the J value. If the fields are parallel, remember the fields are parallel, meaning the electrons are parallel to each other, you have L plus S. But if the fields are parallel, you have slightly higher energy. The fields are anti-parallel, meaning the electrons may be in one orbital, then the S, remember, the sum of the spins equal to 0, you have a slightly lower energy. So this is what this is. If they are parallel, slightly higher energy. And now the second one is here, again, you can have low energy, a low J value, and we define the spin orbit coupling by the letter J. This is why I want everybody to pay attention to. That is spin orbit coupling. The letter J, what do you call J? It's a spin orbit, okay? So J is the total angular momentum as it moves and couples, and the J is given by J equals to L plus S, where L is the orbital quantum number, S is the spin quantum number. All right? Is this familiar? For those of you taking physical chemistry or from Gen Chem 2, Gen Chem 1, that's familiar ground, right? J equals to L plus S. And L, this bigger L, is the sum of the small l's, where you have the electrons in various orbitals. And S, the big S, is the sum of the spins of each of the electrons. And so you only allow for positive values only. So this is like when they're coupling together, you're going to have the north and the north compass together, they repel each other, whereas versus north and south, or south and north. We're just using that sort of analogy here. So let's look at here. It's a vector sum. That's angular momentum J equals to L plus S, all right? That's angular momentum. It's a vector. From mathematics, we know that's a vector. So if L, let's say from L equals to 0, if L equals to 0, that tells you that the electron is in the S orbital. Remember, S orbital, L equals to 0, L equals to 1, that's a P orbital, L equals to 2, that's a D orbital, right? So that's what you have here. So for example, here, if you have an S electron, L equals to 0, S, remember this spin, can be a spin up, spin down, plus a half, or what? Minus a half. That's what we are saying here. S electron has L equals to 0, S half, or minus a half. So the J, remember we take the magnitude, positive values only. J equals to, if an electron is in the S orbital, it is 0 plus a half, or 0 minus a half. But it's the magnitude, it's the modulus. We're together there? So you can only have one by. Make sense there? So which is J equals L plus a half, which is a half. That's for an S orbital, just one electron. And then we have, if the electron is in the P orbital, remember P, the L value, okay? The orbital quantum number for P, the electron is L equals 1, and if it's one electron, then the S equals to a half or minus a half, which means you have two possibilities. 1 plus a half, I give you 3 half. So this is what you have here. L equals to 1, L equals 2, sorry. So if L equals to 1 here, so you're going to have 3 halves or 1 minus a half, that's 1 half. That's the lower energy, okay? Familiar ground, everybody should understand that, I hope, okay? So you have two possibilities there. Now, if L equals to 2, remember, if L equals to 2, that's a P orbital, right? And it's a P orbital, L equals to 2, sorry, if L equals to 2, that's a D. I misspoke there, a D. We're together there. That's an electron in the D orbital, which means L equals to 2, and the P, sorry, the S is plus a half or what? Minus a half. So you're going to add 2 and a half, 2 plus a half, that is the vector, 2 and a half, that gives you 5 halves, right? Or 2 minus a half, that gives you 3 halves, right? Those are the possibilities. And you can have many orientations here. So let's do here something that we normally, you might have gone through, how you write the electronic time symbol. Everybody familiar with the electronic time symbol? So the electronic time symbol is this. It is 2s plus 1. Then you have the L value and then J. Remember, J equals to L, small, it can be capital L, plus S. That is the magnitude. That's what L is, right? J. And 2s, S is the sum. Remember, the big S is the sum of the small s's, which means you can have L as these letters, S, P, D, F, instead of a number. So notice what you have. Let's take an example of lithium. This is the electron configuration of lithium ending in 2s1, which means that electron in the s orbital has L equals to 0, then S equals plus a half or minus a half. Remember, you take the magnitude for J, and that means you can only have one term, symbol. Okay, 2s plus 1 is what we call spin multiplicity. Is that not what we know? Spin multiplicity? True or not? Okay. Now, next, if you excite it, remember, I want to illustrate this before we move on. If you excite this electron in the outermost valence shell, you excite it to have this configuration. Remember, it's a lithium atom. It's not an ion. We're dealing with AA. The electron is in that orbital. You are exciting it to another next higher orbital. So you're going to have this electron configuration 1s2, 2p1. So for P, remember, L equals to 1. Why don't we consider the inner electrons? Some of you may ask.
They already filled.
They are already fully filled. The S equals to 0. So we consider the outer one, the outermost one. So that is 2p1, L equals to 1, S equals plus a half or minus a half. And then you can have 1 plus a half is 3 halves, 1 minus a half is a half, right? But it's L, remember L, capital L, is where this is the orbital quantum number. It is P, L equals 1. So that P, capital P here, and then you have 2s plus 1. Remember, it's 1 electron. Can be 2, 2s, 2 times a half plus 1, right? That gives you 2. That's why you have these term symbols here. Okay? Is that clear, or I need to go slowly here? Everybody knows how to do this, I'm assuming, so that I don't have to hold myself here for long. Is that okay? So if you consider beryllium is 1s2, 2, notice the ground state. Remember, that's the basis of atomic absorption. The ground state, you have the ground state electron configuration for that particular atom. And we're considering just one atom, an electron in the outermost valence shell. So this is 1s2, 2s2, L equals to 0 because it's in the s orbital, and therefore S equals to 0, or notice now that is an S equals to 0. So you have the L term is S. Now you have here two things when S equals to 0. So now calculate the term symbol. It's 1 electron, fully filled, right? Spin up, spin down, right? Minus a half plus what? Am I talking to one of you or not?
Positive.
So plus a half, minus a half. You add them together, it gives you what?
0.
0. So 2s plus 1, right? Remember, 2s plus 1. So 2 times 0 plus 1 is what? 1. That's why you have 1. And then J. J is L plus what? S. Remember, if it is the electrons are in the same orbital, the S is 0 and L is 0. So L plus S is 0. That's why you have that. Okay. Then you go to excited. If you excite it now, you're going to have a little bit more. Excite one electron to the outermost shell. So that means you take one S electron, promote it to the next orbital, which means it's going to be 1s2, 2s1, 2p1. And then now they're in different orbitals. So you're going to have all sorts of, the sum here is S. The S, that's the spin, the total spin is if all of the electrons are up, it just means plus a half, that's 1, right? Or if one electron is up, the other electron is down, then that is also 0, minus a half plus a half. That's why you have these two, S equals to 1, S equals to 0. Everybody's clear about this or not? If not, just raise your hand. Yes, tell me.
Explain how to find L again.
The L, remember, we're using capital L. Capital L is the sum of all the small L's. All right? So I step back a little for you to see. Okay, so the L term here, let me see here. Yep. See here? The L, the capital L is simply the sum of all the L's. If you take, for example, the beryllium here, the electron is in two orbitals. One of them is in the s orbital, the other one is in the p orbital, right? So the total L will be in the s orbital, L equals to 0, correct? In the p orbital, L equals what? 1. So you add the two, right? So 0 plus 1, that gives you an L value of 1, which is P. Does that make sense here? Okay. Then you're going to take the spin multiplicity. Spin multiplicity is defined as 2s plus 1. All right? So you take account of where these electrons are. The electron can be in the s orbital, spin up, or spin down, right? So let's take all these configurations. Let's first assume all the electrons are up, facing up in the two orbitals, all right? That's a half in the s orbital plus a half, right? That gives you a total of s of 1, all right? Then we need to get a spin multiplicity, 2s plus 1, which gives you 2 times 1 times 1 plus 1, which is 3. Does that make sense here? Then you can calculate here with that electron spin up. And then you can calculate what that J, L plus S in that case, because we took a scenario where the electrons are all facing up, one in the L orbital, one in the S orbital, right? And in the L orbital, this one here, all right, because it's L plus S. The L is 1, and then S will be 1. It's going to be, we're going here, J equals to L plus S. So you calculate the total L will be 1, and then the spin, when the two electrons are up, is a half plus a half. All right? Does that make sense now? Okay. So that's how we get to this. So why am I going through this? I'm just doing this to give you an idea. On the next side, the next thing I want to show you is when you have these electrons, remember we are just exciting the electrons in the atom. We are not making ions in atomic absorption. We're simply exciting the atoms, and the electrons are in different orbitals. So if you have a thing like this one here for beryllium, you have so many terms. What these terms correspond to are the lines that we choose. And this is where we have, for example, a sodium line. You have these terms here. You can calculate, verify for yourself. For sodium, remember the sodium is 3s1. You have only one electron, right? You can calculate the term. It will be 2s half. Anybody you can calculate this, right? Sodium. So it ends in 3s1. Okay. The spin is going to be plus a half or minus what? Half. 2s plus 1 is going to be 2 times a half plus 1, which is simply 1 plus 1 equals to 2. Does that make sense there? So that's the number you are getting. This is the number you are getting here. And it's in the s orbital. That is, remember, 3s1. That's the s orbital. We have only one electron. That's an s term. Does that make sense? And then for L, the L value is simply the sum. L, it is in the S. Remember, J equals to L plus S. That's a magnitude, whether it's positive or negative. So it's going to be half plus 1/2. Here, it's not a half. It's going to be the L is going to be what? 0, because it's in the s orbital. Does that make sense? So you add the 2, you get 1/2. And this is what you have here. And then you can excite it and calculate the others. Does that make sense? Okay, so that is in this one, the ground state has only this symbol, the time symbol, 2s². Then you excite it to the p orbital, 1 electron from the 3s1 to the 3p, so which means the p, the L value is 1. That's why you have a p state, all right? It's 1 electron, so the spin is only plus a half. Does that make sense? So you can have plus a half or minus what? Half. Does that make sense? Plus a half or minus a half. Then you can do the same. We find it a p, and then now you get 3 halves and 1 half. J equals to L plus S, right? L is 1 plus a half. That gives you 3 halves. Or L equals minus a half. 1 minus half. That's why you get these two. Does that make sense? Remember, I'm going through this quickly so that we get to that, okay? Class, is that clear?
Time state has a 2. Ground state only has 1 S version. So instead of like plus a half, but it looks like
Okay. For the ground state, remember this one here, you take the magnitude. J is simply a magnitude of L, only positive values. Yes, only positive values. Okay? Okay, so here what we know is this particular information is relevant here in the sense that all these lines, all these term symbols correspond to the energies. These correspond to the energies that we measure. And they can be measured. You see the lines here, in the line for you to see. See, this is the line for sodium is a yellow flake, and you're going to see those lines when you take a photographic picture in the lab. This is how it was started. So you're going to see those lines, and you can measure the electron volts that corresponds to this, which means if you excite the 3s electron to 3p, you can have two of those. You can excite it to the D, you can excite it to 4s, you can excite it to 3d. So you have so many lines to work with. Does that make sense? It's just simply a simple illustration of that what happens. So here is what we come up with. So remember I said we choose resonance lines. This is what I want everybody to understand. It's not only one line. So you are having it with sodium. See, that is the one we went for. 2 states. The 3 halves, P 3 halves and P half. We're together. Those are the ones here corresponding to 589 nanometers. The other one, 589.6 nanometers, or this one here. So, and there are so many others. You can excite it to the 4P, the 4D, and so you can choose very many lines. Remember, we talked about spectral interference, because other elements can have the same energy, so you have to choose which one is not going to be interfered with. And we know by working with AA for many, many years, that is what happens. People have worked with this. For magnesium, the same, you can see. And all that I'm saying here for today's class is that you can actually have all these lines. Does that make sense? So when we come back from the break, the exam covers information up to what I've covered here. I summarized AA and so conceptual questions, all right? So I want to ask calculations here. I'll let you know if that, but I won't, okay? That's how it's going to cover the exam. It's on Monday, 16th, right? Yep. Have a good day and a good break. If you haven't got your lab reports, you can come by, but I sent to everyone. Yes, we have recitation in the afternoon. Please turn on your lab reports. Thank you. Did you see your grade?
Work is fine.